start first. Electric potential energy of two charge system in an external field. The meaning is, last class we have learned what is the meaning of electric potential energy. Let me define again. The electric potential energy is what? It is the energy to form a system. It is the energy to form the system in bringing all the charges from infinity and place them at their respective places. That is the definition. Got? So here in the last definition only we have taken a charge system. But what is the difference between the two? Here there exists one electric field which is represented by this arrow. And this arrow that represents non-uniform electric field. By simply I have taken a non-uniform electric field. So one field is already there. You have to take two charges, charge 1 and charge 2. Let's say the charge 1 is Q1 and the charge 2 is Q2, and you are placing them at point 1 and point 2 inside this electric field. Inside this electric field. So you need to find out how much work you need to do, and that work gets stored in the form of electric potential energy there or in the system. So what I have taken, I took one electric field, external electric field. I have chosen two different points, 1 and 2. Here the charge Q1 is to be placed, and here the charge Q2 is to be placed, while bringing them from infinity and placing at their respective places. Late at this point in space, at this point V1 is the electric potential because of this external field. Try to understand here. Because of this field, the potential whatever here, that is V1, and the corresponding value of the potential at point 2, let it be V2. And let's say the distance between these two is R12, what I have taken here. Now, according to our definition, the potential energy of the system means Q1, Q2. In this field, the potential energy will be W1 plus W2. Why W1, W2? W1 is the amount of work done in bringing this charge Q1 from infinity and to place it at this respective point 1. And W2 is similarly, it is the work done in bringing the charge Q2 from infinity and to place it at point number 2. So the total work done will be the potential energy of the system. Got? Now, according to our definition of your potential energy, or potential energy is linked with your work done, like we know W is equal to V into Q. Let me remind you this formula. What is that formula? Suppose at a particular point the potential is V. You are bringing a charge Q from infinity to this point. It's a simple point charge Q. You are bringing to a point charge to this point where the potential earlier it is V, and you are taking that point charge Q from infinity and placing it at this point. So the amount of work done is how much? The potential here, that is V, multiplied with the charge which is being brought from infinity to this point. So your work done will be V into Q. In the same logic, here W1 will be the potential whatever exists at that point 1. That is, I took it as V1 multiplied with the charge which is being brought, that is V1 into, that you can say it will be Q1. W1 is equal to V1 into Q1. That is your W1. Now, let us go for W2. W2 means similarly, we need to find out the work done. Means, let us find out the potential here. See, I have already written here V1 and V2 are the potential because of potential at these 2 points because of the external field. Now, while calculating the potential at point 2, you must remember one thing. Because of the external field, the potential was V2, and you are bringing a charge q1 and already placed here. You have already brought and placed that charge q1 at point number 1. So the total potential will be what? The potential because of the external field plus the potential because of this charge which is already placed inside that field. So we have taken here W2 according to the same formula. W2 is what? The potential at point number 2 multiplied with the charge which is brought from infinity and it is placed here. So the net potential will be the sum of two potential. One for the external field and the second one for the charge which is already brought. Now this is V2 plus, what is this value? See, this Q1 is a point charge, and for a point charge the potential at certain distance will be given by V is equal to 1 by 4 pi epsilon naught Q by R. It is the general formula for a point charge. So that's what I have mentioned here. See, V due to Q1. So which is 1 by 4 pi epsilon naught Q1 by R12. Using this formula, because this Q1 is the charge here and the distance from 1 to 2 it is R12. So formula is 1 by 4 pi epsilon naught Q1 by R12 whole multiplied with Q2. So your total work done will be what? W1 plus W2. You add. So first term is V1 Q1 that you can take. The second term is V2 into Q2. Yes. V1 Q1 plus V2 Q2 plus 1 by 4 pi epsilon naught Q1 Q2 by R12. So it is your total answer. So this amount of work done gets stored in the form of potential energy. So your W, you can take it, and W is nothing but your U system. So we can write here W1 plus W2 is equal to W, which is nothing but your U system. So here instead of W we can write it is the potential energy of the system. Got? Now let us calculate the electric potential energy of an electric dipole in a uniform electric field. See, this can be done in two ways. So let us first find out this in a simplified manner. Suppose there is an electric dipole. It is placed in a uniform electric field E. Here it is minus q charge, it is plus q charge located, and the dipole moment is directed from negative to positive charge. So it is the direction of dipole moment here. I can take it to be p vector. Let theta be the angle between the dipole moment and the external electric field. Got? Suppose I am interested to rotate the dipole inside the electric field from an angle theta 1 to theta 2. Let theta 1 is the initial angle and theta 2 is the final angle between the dipole moment and electric field. See, why here we will be calling this your dipole's potential energy. See, on the dipole, when a dipole is placed in an electric field, it experiences a torque. In your previous chapter, we have learnt this. And the magnitude of the torque is given by tau is equal to Pe sin theta. P is the dipole moment, E is the magnitude of the electric field, and theta is the angle between the electric field and the dipole moment. Now see, suppose you are rotating it, and this torque will try to tend the dipole, try to align the dipole along the direction of the field. Means this is the torque by the field exerted on the dipole to keep the dipole in its orientation. Is it clear? Suppose you want to rotate it and rotate it from theta 1 to theta 2 position in the field opposite to the torque. Means what? Means you need to apply, the external agent need to apply this exactly this amount of torque if you want exactly this amount of torque if you do not want to change the kinetic energy of the rotation of the dipole. So in that case you have to apply equal magnitude torque and oppositely directed so that you will rotate the dipole to your desired position. Now suppose you have applied equal amount of torque. This is the torque exerted on the dipole because of the field. Exactly same amount of torque you have applied, means external extent applied to rotate the dipole. Suppose there is a very small rotation. Suppose in this angle you have slightly rotated by an amount d theta. Then the amount of work done will be given by dw is equal to tau into d theta. Work done will be torque into your angular displacement. Theta is what? Your angular displacement. So dw is equal to tau d theta. So tau is equal to Pe sin theta. Now your dw will be Pe sin theta d theta. See, here torque is a variable one, because if you rotate slightly the angle theta is going to change. So your torque is going to change here, means it's a variable torque. So in the case of a variable torque, your total work done will be integration of dw, that is 0 to w limit. Because your initial position, suppose that theta 1 position no work is being done, and you are rotating it to the final destination where the angle is theta, and there the total amount of work done will be w. So that's why corresponding limits I have taken here, because I have replaced the dw Pe sin theta d theta, and here the variable is theta. So the limits of the theta is theta 1 to theta 2. Now P and E both are constants, it is taken out of the integration. So integration of sin theta d theta, limit theta 1 to theta 2. P is a constant here. So integration of sin theta is minus of cos theta. So minus of cos theta, the limit is from theta 1 to theta 2. So I took the minus outside. So which is minus Pe, and I put the limit here, cos theta 2 minus cos theta 1. Now you see, I have again multiplied this negative with the in this term. So your term will be Pe. This is see, minus cos theta 2 and minus of minus plus cos theta 1. So Pe whole into cos theta 1 minus cos theta 2 is your W. Now there is a special case. Suppose you have rotated the dipole from its zero energy position to any desired position theta. Means we are actually dealing with, we need to find out if the angle between the dipole moment and the electric field is theta at a particular position, then what is the potential energy of the dipole? Clear? So in that case, your initial angle theta 1, it is your pi by 2, that position is called your zero energy position. And your final angle, we can take it to be theta 2, which is your theta. So that is, at this position you need to find out the potential energy. Now you can substitute for this. So theta 1 pi by 2, theta 2 theta. So I have substituted here. So Pe cos pi by 2 minus cos theta. Cos pi by 2, this tends to 0. So which is minus Pe cos theta. Now see here. So the potential energy is nothing but the work done here, and which is given by minus Pe cos theta. Clearly, it is why this position is called your zero energy position. From this equation, it is very clear. Because if you put theta is equal to 90 degree, then at that position, the potential energy or the work done or the potential energy will be 0 there. That's why that position is called your zero energy position. Or otherwise, we can explain this zero energy position to be like, suppose, see the diagram, in which position the your angle is 90 degree. This is dipole moment and this is electric field. Means, let's say, if you take here, this point to be here, then your dipole moment will be in this direction and electric field will be in this direction. So this will be the position of minus q and this will be the position of plus q. Why that position is called your zero energy position? Let us understand here. Consider these 2 points. Because we are taking theta 1 to be pi by 2 is your zero energy position. So this angle is 90. Let us take these 2 points. Now, if this dipole is brought from infinity and the 2 charges are placed respectively at these 2 points, then let us find out how much work will be done. Try to understand here. See, as it is a uniform electric field and these 2 points are lying perpendicular to the field, these 2 points potential are equal. Try to understand here. Here the potential is V, so, and here also the potential will be the same, V. Let us consider the potential both at both the places, let's say it is V, because as these 2 points are lying on a perpendicular line, means these 2 points, the points means what? This plus Q and minus Q charge is located at 2 points which is perpendicular to the electric field, or they are actually lying on a particular line, and that line is perpendicular to the field. So according to our definition, the potential at these 2 points must be same. So the total amount of work done will be how much then? Total amount of work done will be W for minus Q and W for plus Q, means you are going to bring positive charge plus Q charge from infinity and to place it here, negative charge bring it from infinity and place it here. So you need to find out the total work done. Now W minus Q, that I can say V into minus Q, because the potential at point is V and the charge magnitude of the charge is minus Q, plus the potential at that point will be again V and the charge is plus Q. So the total amount of work done is 0, and which is your potential energy, U. Clear? Means at this position, if you want to place the dipole in bringing it from infinity and place it here, your total amount of work will be 0, which is your potential energy. That's why we took theta 1 to be pi by 2 will be your 0 energy position. Got it?